Hi, everyone. I'm recording chapter 4 lectures today. In chapter 4 and chapter 5, these two lectures, we're going to study them together. And in these two chapters, we're going to focus on chemical bonds. Okay, basically, we're going to focus on how atoms or ions are held together to build up more complex units, such as molecules and other complex compounds. And that holding force is called chemical bonds. And regarding the ways atoms bonding together, okay, holding together, we usually have three types. Okay, those three types are called ionic bonds, covalent bonds, and metallic bonds. Okay, metallic bonds. Usually, metallic bonds are bonding for metals. Okay, bonding for metals, and we don't discuss that within the scope of your class because that's mainly discuss element metals. Okay, how metal atoms are bonding together is a more complex theory. So in this class, what we're focusing on will be ionic bonds and covalent bonds. And again, no matter what type of bond, bonding forces are the purpose of holding atoms together. And what's more importantly, the forces, no matter ionic bonds or covalent bonds, is the result of electrons. It is the electron behavior that holding atoms together. That also can reflect something we have said earlier. In chemistry, the atoms are the smallest entity, okay, in this subject. And atoms don't change during chemical reactions. They simply rearrange. So what happened is that behavior of the electrons, not the atoms themselves, or to more specific, not the nucleus themselves. Mostly is the electrons. There is the behavior of the electrons resulting in some electrostatic forces holding atoms particles together. Okay, like I said, we have two chapters discussing these chemical bondings. Okay, in chapter 4, we're going to talk about the bonding resulted from transfer of electrons from one atom or one group of atoms to another atom or to another group of atoms, and resulting in some electrostatic forces between the charged species, because after you transfer electron, you were getting some charged species, and we call them ions. And because of that, the bonding in this chapter 4, we call ionic bonding because they're ions. And compounds in this chapter from ionic bonding are called ionic compounds. And that's what we're studying in chapter 4. In next chapter, we're going to study bonding formed from the sharing of electrons instead of transferring. They're not given, they're sharing. And compounds resulted from sharing electrons are either called molecular compounds, means they are molecules, or covalent compounds, means the atoms are bonded through covalent bonds, and there are a huge network of covalent bonds. We call them covalent compounds. So these are the compounds from covalent bonding. Okay, that's why we have two chapters talking about these concepts. But you should keep in mind, even though we're talking about these two types of bonding, they're different. One is transfer, one is sharing. But there's no definitive cut line limit on what type of bonding is in which type of compound. Or in another word, there's no bond that is 100% ionic or 100% covalent. It is always some degrees. Okay, some degrees. We'll see this chart later on, okay, in our later chapters, but in chapter 5, I think. But the idea is the type of bond depends on what? Depends on a continuous difference between these two atoms. Okay, later on, we know they're called electron activity. So as the difference of these two atoms changes, the type of bond will change, but there's no cut-off lines. Okay, you can see the type of bonding, ionic, including a covalent and ionic. These bondings are in a continuous spectrum. Okay, so again, even though we study these two extreme types, you should keep in mind the bonds are not pure ionic or pure covalent. We just study these two types and be able to explain some properties of the compounds. Okay, so without further ado, let's take a look. Chapter 4, chemical bonding, ionic bond model. Okay, it is a model that said there's no definitive type of bond. There's no bond is called a pure ionic bond. It just has more ionic bonding character. And we know, again, ionic bond is the result from the transfer of electrons. So this chapter, we're going to take a look. What is the transfer of electrons? What electrons are transferred? Are all the electrons transferred or some of the electron transfer involved in this bonding? Okay, this is the overall structure of the chapter. Like I said, 4.1, the bonding intro we have already talked about. So in this chapter, we're going to talk about the concept called valence electrons, Lewis structures, the octet rule, and also talk about the ionic compound, including their formulas, the structure, their naming, and also we're going to talk about a special group of ions called polyatomic ions. Okay, polyatomic ions here. So this is the overall structure of this chapter. Let's get started. When we talk about bonding, no matter ionic or covalent bonding, there are two fundamental rules. Okay, these are the fundamentals of chemical bonding. One rule is not all electrons in an atom participate in bonding. Remember, we know the electrons of atom, the number of the electron equal to the proton numbers. But no matter how many electrons there are, not all electrons participate in bonding. Only a small number of electrons are involved in bonding, and we call those electrons valence electrons. Okay, first, you know, valence electrons are the one involved in bonding. We're going to talk about valence electrons right away. That's the first fundamental. And the second fundamental is electrons tend to arrange, no matter the transfer or share, they tend to arrange in a certain way so that the resulting species are more stable than before or more stable than original. And that special arrangement to make them more stable doing transfer or sharing is called the octet rule. Okay, the octet stands for 8. So there are some 8 electrons playing in here. We're going to see that. So these two are the fundamentals of chemical bonding. Valence electrons that are involved in bonding, and also electrons tend to arrange into a more stable format called the octet. Okay, called the octet. So let's take a look. First, what are valence electrons? Okay, what are valence electrons? That is said, like I said, not all electrons in an atom are involved in bonding. Only a small group. And that small group of electrons that are involved in bonding are the electrons in the outermost shell, or the highest energy level. Okay, highest energy level. And we have studied in chapter 3 that the highest energy level equal to the period number. If you are a third period element, for example, then your highest energy level will be 3. If you're a fourth period element, your highest energy level will be 4. But regardless, the electrons in the highest energy level are called the valence electrons. Especially, like I said, for representative elements, group 1 through 7A, and noble gas elements. These elements, their highest energy level electrons are called the valence electrons. So here you can see there are 3 electron configurations: magnesium, silicon, and arsenic. Okay, magnesium, the highest energy is 3. So those 2 electrons in magnesium, third level, is the valence electrons for magnesium. Silicon, the highest energy level is 3. The 4 electrons in the highest energy level are called the valence electrons for silicon. Okay, arsenic is the fourth group element, first period element. So the highest energy level is 4. So those 5 electrons, including 4s2 and 4p3, those 5 electrons in the fourth energy level, the highest one, are the valence electrons for arsenic. So you can see that electrons in the highest energy level are the ones that are involved in bonding, and we call them valence electrons. Okay. And here is the part of the periodic table showing you the main group element, including the representative element from group 1A through 7A, and also the group 1A noble gases. And you can see their electron configuration of the highest energy level listed in this part of the periodic table. For example, the electron configuration for lithium is 2s1. That means their highest energy level is 2s1. Okay, the highest energy level for phosphorus is 3s2 and 3s2 and 3p3. So total 5 electrons in the highest energy level. And if you look at these the electron configuration of the highest energy level of these main group elements, you will notice something very interesting. That is the number of the valence electrons actually the same in the whole group. If you look at the first group, the valence electrons in the highest energy level is 1. If you look at the second group, the number of valence electrons for the electron in the highest energy level is always 2, and so on in the other groups. That's something you probably didn't notice. Another thing, also you didn't notice that the number of the electron in the highest energy level, the valence electrons, actually equal to their group number. Okay, for example, group number 3, okay, again, we're using that bottom number system, okay, 1A through 7A system. Okay, for group 3, the number of electrons in the highest energy level is 3, right? 2s2, 3p1, 3s2, 3p1, 4s2, 4p1, total is 3 electrons. And the same for group number 8, the number of electrons in the highest energy level is 8, 2s2, 2p6, 3s2, 3p6, except helium. Helium only has 2 electrons, so that's an exception. So what do we know here? Representative elements and noble gases in the same group have the same number of valence electrons. The number of valence electrons for these elements equal to their Roman number, group number. That means group 1A through 8A. Okay, the AB group number notations. Okay, the number equal to the group number. And the maximum number of valence electrons for any element is 8, 2s2, 2p6, 3s2, 3p6, right? ns2, np6. And then you move on to the next period, it go back to 1 now. Okay, 1, 2, 3, 4, 5, 6, 7, 8. And then go back to 1, 2, 3, 4, 5, 6, 7, 8. So the maximum number of these elements, of the valence electron of the elements is 8, which are the number of valence electrons for these noble gases. So these are the 3 very generalizations about valence electrons. Again, these are the electrons for chemical bonding. Okay, here's a concept check. Again, you can bring out your periodic table, pause the video, bring out the periodic table, and see how many valence electrons for these elements. Calcium, if you look in the periodic table, is group 2A element. So 2A, 2 valence electrons. Okay, the highest energy level is 4. So 4s2 calcium, if you notice that. Okay, selenium, Se, is group 6 element. Okay, guys, take a look. Here's selenium. Let me erase them all. Okay, selenium is group 6 element. So 6 valence electrons, 2s2, 2p4. Okay, 4s2, 4p4, sorry, because selenium is group 4 element. And finally, carbon, easy. Okay, group 4 element. Okay, so valence electron is 4, 2p2, 2s2, 2p2. Okay, so again, use the periodic table to play with and determine the valence electrons in a very quick way, right? Now, after we know the number of valence electrons, and also we know these electrons are important for chemical bonding, so we invented a symbolized version showing these electrons, because these electrons were involved in chemical bonding. And we call that symbolized version Lewis structure. In Lewis structure, electrons are shown, valence electrons are shown as dots, okay, as dots surrounding the symbol. Of course, we're only showing the valence electron, not all the electrons. Okay, that means lithium, potassium, hydrogen, you can see group 1A, these elements, they only have 1 dot. Group 3A element, boron and aluminum have 3 dots because their number of valence electrons is 3. Okay, group 7A element, their number of dots is 7 because they have 7 valence electrons. So we use the dots equal to the number of valence electrons to show these atoms because, again, these dots are involved in bonding. Okay, involved in bonding. And that's called Lewis structures. Okay, Lewis structures. And this is a quick practice, asking you to draw the Lewis symbol for these elements. Please, even I give you the key here, I will hope you to cover the key and draw the structures. Okay, oxygen, for example, has 6 valence electrons because oxygen is group 6 element. So there's 6 dots around the oxygen. See that? And 2 in pairs. Okay, normally we draw the electrons in pairs unless there's odd number. Okay, phosphorus, group 5 element. So there are 5 dots. So 2 in pairs, 1 is single. Okay, fluorine is group 7 element. So there are 7 dots. See that? 3 pairs plus 1 single. Okay, again, practice drawing, even though it looks simple, but I hope you can put on paper because there are assignments and tests ask you to draw these structures. Now, after we know the number of valence electrons, we also know a very important fact that the maximum number of valence electrons is 8. That is the noble gas, right? The configuration noble gas, NS2 and P6. And we also know that noble gases are stable. The reason they're stable is, again, because their valence electron is 8. Why they're stable? Because all these noble gases have the maximum number of valence electrons, 8. That's why they're stable. So because of this fact, okay, because of the fact, atoms, other atoms that are not noble gases will try to lose or gain or share electrons to achieve an 8 valence electron configuration in the formation of compounds. Okay, in the formation of compounds. And that process, that rule is called the octet rule. What is octet? It is the achieving of what? Of 8 valence electron configuration, like noble gas, during the formation of compounds. Through what? Through losing electron, gaining electron, or sharing electron in a way, so that they all end up with what? 8 valence electrons configuration. Again, configuration. You don't become another noble gas. You just achieve the configuration, because remember, what is changing is only the valence electrons. The nucleus themselves are never touched in chemistry. Okay, you're only getting that configuration. That's what we call octet, 8 valence electron configuration. Now, in this chapter, like we said, we're talking about the achievement of octet through losing or gaining electrons. So what happens when an atom loses or gains electron? We know atoms are neutral. Okay, are neutral. But when they lose electrons are negative. So when you lose something negative, you will become charged, or you gain something negative, you will also become charged, because originally all atoms are neutral, same number of proton and electron. So in the process of losing or gaining electrons, atom will become something charged. We call those charged species ions. Okay, ions. When atom loses electron, that means you have more proton than electron. So atoms will become positively charged. And we call the positive charged ions cations. Okay, cations. For example, sodium. Sodium has 11 proton, 11 electrons. If you lose 1 electron from sodium, then sodium ion will have 11 proton and 10 electron because you lose 1. So overall, you have a what? Positive 1 charge. Okay, you will have a positive 1 charge because proton now more than electron. And on the other hand, if you gain an electron, for like chlorine, Fluorine has 17 electrons, 17 proton. But if you gain electron, you get 18 electron and 17 proton. Then you have one more electron. So you get a -1 charge. And those -1 charged species are called anions. Anions. So you can see that atoms losing electron will always become positively charged cation, and gaining electrons will always become negatively charged anions. Okay, this is what happened when atoms gain or lose electrons. But the question is, how many electrons are lost or gained for an atom? How do I know that? And how come losing or gaining electrons achieve noble gas configuration? What is the logic behind that? Let's take a look. This is the noble gas configuration of sodium. 1s2, 2s2, 2p6, and 3s1. We know sodium is group 1 element, third period. So the highest energy level is 3s1. Okay, it's 3 and 1 electron, so 3s1. You can see that sodium, because of 1 electron, in order to achieve noble gas configuration 8, it has 2 options. One is lose that 1 electron in the third shell. So after losing, you said the outside becomes what? 2s2, 2p6, right? There's no 3s1 anymore. And that is noble gas configuration of the neon. Configuration, again, not neon, just become the configuration of neon. Or in another way, instead of losing 1, it gains 7. 1 plus 7 is 8. So the outermost shell becomes 3s2, 3p6. That also can work. But, okay, you know that. Losing 1 will be a lot easier than gain 7, right? Just take 7 and you just lose 1. So what sodium does is very simple. Lose that single electron on the third shell, so the second shell becomes noble gas configuration of neon of the previous period. Okay. Sodium is the third period. Neon is the second one because you lose a shell. So sodium losing 1 electron. Why? Because sodium has 1 valence electron. Okay, 1 valence electron can only lose 1 to become noble gas configuration. And when you lose the electron, of course, you become positively charged. The charge will be indicated as a superscript. Okay, potassium, for example, K plus superscript. Sulfur, the charge will be negative, also superscript. By convention, we put the magnitude 2 first, followed by the negative. Okay, sulfur 2 minus. Okay, the charge must be superscript. Okay, I want to remind you, when you're doing your quiz or tests, in the answering box of Blackboard, there are, like a Word document, there are ways to change a number or a sign to a superscript or subscript. Charge must be superscript, form a good habit. If you're not subscript, you will maybe have credits off because of that. Now, because we want a correct chemical language, charge are indicated as superscript. And by convention, the magnitude of it is spelled first. So S2 minus for sulfur. Okay, so now you know the logic of becoming noble gas configuration by losing or gaining. So let's take a look. What other charges we're expecting for our representative elements? Okay, we have 3 guidelines. The first guideline is group 1, 2, and 3 elements. These are metals, mostly metals. Because they have 1, 2, and 3 valence electrons, they tend to lose 1, 2, or 3 valence electrons. It's easier, losing electrons, to become a noble gas configuration. The noble gas configuration will be the one preceding the metal because they're losing a shell. So third period will become the noble gas configuration of the second period. Fourth period will become the noble gas of the third period. And the corresponding charges will be +1, +2, +3. Group 1A lose 1 electron, charge will be +1. Group 2A lose 2 electrons, charge will be +2. Group 3A, 3 valence electrons, the charge will be +3. These metals will lose electron to become the noble gas configuration preceding the metal in the periodic table. Now for group 5, 6, 7, instead of losing electron, they will gain electron to become noble gas configuration of 8. 5, you will gain 3. 6, you will gain 2. 7, you will gain 1. So the charge of group 5, 6, 7 will be what? -3, -2, and -1. Because it's easier for them to gain electron. And after gaining electron, they become a noble gas configuration of the same period in the periodic table. I mean, following the nonmetal in the periodic table. Okay, those are the charges for group 5, 6, 7. Okay, the charge number are negative. Group 5 is -3. Group 6 is -2. Group 7 is -1. For group 4 element, because they have 4 electrons, it's hard for them to either gain or lose. So most likely these elements will achieve noble gas configuration through sharing instead of really giving or losing, or giving or gaining. Okay, that's the topic of chapter 5. Okay, so normally you don't see ionic bonding for group 4 element because again, they have 4 valence electrons. Okay, so this chart summarizes what we have talked about, the common ion charges for metals and nonmetals. Okay, again, the ones that are in common and seen, we listed in this chart, including the charge and also the sign and also the magnitude. Okay, you can see that the metal will have a positive charge. The charge number is the same as group number, group 1 + 1, group 2 + 2, group 3 + 3. The nonmetals will have a -1 charge, negative charge. Group 5 is -3, group 6 is -2, group 7 is -1. Okay, how do we calculate or how do you memorize? My rule is the group number -8. If you notice that. If group number 5 -8 is -3, group 6 -8 is -2. So for nonmetals, you simply use the group number -8, you get the charge number. Okay, you get the charge number. Again, the charge is a superscript, and we spell the magnitude first, followed by the charge. So calcium 2+, sulfur 2-, and aluminum 3+, right? Not +3, 3+ by convention. So this chart will be very useful. Okay, now, remember, no matter metal or non-metal, they lose or gain electron, they become what? Noble gas configuration. Metals become the one previous, in the previous period. Non-metal become in the same period. So for some metals and non-metal, when they gain or lose electron, they may end up with the same electron configuration, which is the noble gas. For example, these ones, these are the ions. That means they're after the gaining or losing electrons. Okay. Nitrogen, oxygen, fluorine, they gain 3, 2, 1 electrons. Sodium, magnesium, and aluminum, they lose 1, 2, and 3 electrons. But they all end up with the same configuration of what? Of neon, which is 2s2, 2p6. Okay, that means they all have 10 electrons for these species. Okay, these 3 ions, anions, nitrogen 3-, oxygen 2-, fluorine -, or sodium plus, magnesium 2+, and aluminum 3+, they all have 10 valence electrons. Okay, they all have 10 electrons after losing and gaining. They all have 10 electrons, which is the same electron as what? As neon. And we call those species with the same electron configuration, we call them isoelectronic species. But again, keep in mind, all these species, they are the same electron configuration as neon, but they are totally different species. Okay, because their proton numbers and neutron numbers are totally different. The only thing that's the same is what? They all have the same electron configuration. That's the important thing. And we call those isoelectronic species. Okay, how do we find isoelectron species? You look at the noble gas, for example, neon. Then the nonmetals before it and the metals after it will make isoelectronic species if you convert them into ions. Okay, if you think about that. Because metal will become the noble gas in the previous period. Non-metal will become noble gas of the same period. So they all end up with the same neon. Okay, nitrogen, oxygen, fluorine is right before neon. Sodium, magnesium, aluminum are right after neon. Okay, they will make isoelectronic species. Okay, with that logic, I hope you to practice this. Okay, choose a metal, alkali earth metal, a noble gas, a halogen, means group 7, group 1, and group 2, and group 8, and make a group of 4 isoelectronic species. Okay, when they become their ions. Of course, isoelectron species, the metal and non-metal has to be ions. Okay, to write the ions with the noble gas and see how many electrons are there, what the electron configurations, and also how many protons are there, how many electrons there, everything. Okay, I want you to use that logic. Okay, this is one example, neon, and some elements behind and after neon. Then you choose another one. Okay, write 4 isoelectronic species and ask yourself, what is the electron configuration? What is the charge of each one? And what is the number of electrons for each one? Of course, they're isoelectronic, that means the charge will be the same. The number of electrons will be the same. And also what the proton numbers are for each. All right, so practice, please. Okay, next, after we know atoms will lose or gain electrons to become ions. And then let's take a look at the formation of compounds in this chapter called ionic compound. What is the formation of it? How do we get ionic compound? One thing we didn't mention earlier was the formation of ion. That means gaining or losing electrons are not isolated or singular process. That means you don't just lose one electron or you don't just gain one electron. They normally happen simultaneously, meaning if you want losing or gaining electrons, you must have a metal normally that lose electron. And you also have a non-metal that actually takes the electron lost by the metal. You see that? That means you have 2 parties, one party losing electron, another party gaining electron. And those 2 happen at the same time. So electrons are not really lost. They're lost by the metal, but gained by what? By the non-metal. So instead of normally saying losing or gain, we're actually talking about what? The transfer of electrons. Okay, electron transfer. So electron lost by the metal are normally gained by the non-metal. That's how we realize transfer. For example, sodium. We know sodium is group 1, losing 1 electron. Chlorine is group 7, gain 1 electron. So sodium lose 1, gained by chlorine. Both of them become what? Noble gas configuration. See that? Sodium becomes sodium plus, chlorine becomes chlorine minus. And chlorine minus and sodium plus, they're oppositely charged, so they like each other. They will attract each other to form what? To form ionic compound. So this is very easy. What is ionic compound? Ionic compound is basically after the transfer of electrons, both atoms becomes ions attracted to each other now. Okay, later on, we're going to see how they attract, how they arrange those ions, okay, in a structure. But this is the basic of Lewis structures. And this reaction sequence is the formation of ionic compound using Lewis structure. I want you to know the details about the sequence and be able to write the sequence by yourself. 2 arrows, 3 steps, or 3 species, 3 group of species. But you have to use the same format, be able to represent the formation of ionic compound. All right, let's go over this sequence. First, you have a sodium with 1 dot, because sodium is group 1A element. You have a chlorine, 7 dots, because chlorine is group 7 element. So sodium lose that electron and then transfer it to chlorine. You see that there's an arrow showing transfer. So sodium becomes sodium plus, no more valence electron. It's gone, that one is lost. But chlorine now has what? 8 valence electron because it gained one extra. So chlorine is minus. So that's what sodium and chlorine become after the transfer, after losing and gaining. Then you have these two species, these ions will attract each other. So the formula for sodium and chlorine, and we call sodium chlorate, is NaCl. The ratio of these two is 1 and 1. Why? Because one lose one, one gain one. You don't need others. It's 1 and 1 ratio. And that is how you represent the formation of sodium chlorate using Lewis structure. Again, you have to get used to this whole sequence, what you need to draw, what you need to put, and what arrows. Okay, sodium, chlorine, transfer, ions, and then the formula, right? And take a look at another example. Here is the formation of a compound between sodium and oxygen. Okay, we know oxygen has 6 valence electrons, group 6 element. Sodium only has 1. So in order for oxygen to gain 2 electrons to become 8, you need what? You need 2 sodium. So that's why I draw 2 sodium here. Each sodium has 1 valence electron, and again, oxygen has 6. So each sodium gives 1 electron to the oxygen. Sodium becomes sodium plus, sodium becomes sodium plus. And oxygen, of course, after gaining these 2 electrons, oxygen becomes 2 minus, because you gain 2 electrons, 1 from each sodium. So that's the ions after gaining and losing. And the formula, of course, will be Na2O, because 2 sodium per 1 oxygen. Okay, sodium. So the ratio is 2 to 1 for sodium oxide. Again, you have to know the exact sequence, and you have to show the exact sequence if you're asked to represent the formation of ionic compound using Lewis structures. Okay, I would know that if you watch this video or not when you show your work in your test and quizzes. Because if you watch the video, you know I emphasize that you need to use the same sequence. Draw the Lewis structure of the atoms, show the transfer, show the ions, and then show the formula, 2 arrows. Okay, one more example. Here is the formation between magnesium and oxygen. Oxygen has 6 valence electrons, magnesium has 2 valence electrons, so they're perfect for each other, right? Magnesium loses 2 becomes magnesium 2 plus, oxygen gains 2 becomes oxygen 2 minus. Of course, magnesium has no valence electrons, oxygen has 8 valence electrons. And after that, the formula of magnesium and oxygen is 1 to 1 ratio, because one donates 2, one accepts 2. So MgO, okay, magnesium oxide. Okay, again, you can see that the same format, right? Atoms, transfer of electrons, the ions, and then the formula. Please use the same formula. Okay, here's more. Okay, here's more example. Okay, between calcium and chlorine. Okay, chlorine has 7, calcium has 2. Okay, in order for calcium to donate those 2, you need 2 chlorine to take those 2, because each chlorine can only take 1. So calcium becomes calcium 2 plus, chlorine becomes chlorine minus, and you have 2 of it. So the formula is CaCl2, because 2 chlorine per calcium. Okay, and this is another one between sodium and nitrogen. Okay, 3 sodium, 1 nitrogen, because nitrogen is 5, so it needs 3. Each sodium gives 1, so 3 sodium gives 3. And the ratio will be Na3N. Again, show the whole sequence if you're asked to show the formation of ionic compound. Okay, I've said many times, hope you guys watch the video and know that. And with that, please practice with this one, a little bit more tricky work, a little bit more arrows to draw, but the same format shows you the formation of aluminum sulfide, or the reaction between aluminum and sulfur. I even give you the number. Okay, aluminum has 6 valence electrons. Aluminum has 3. Sulfur has 6. So each sulfur takes 2. in order to for this work, you need 2 aluminum and 3 sulfur. Okay, 2 aluminum gives 6 electrons. 3 sulfur gains 6 electrons. Think about it. Okay, and then again, use the same format I'm doing here. The atom, transfer, ions, and then formula and 2 arrows to show the formation of aluminum sulfide. Okay, please practice after you watch the video, or you can stop the video or pause the video and practice on your scratch paper. Okay. Now, all these compounds we have seen and draw the structure and draw these formations, you notice that it contains 2 elements, right? 2 types of atoms. One is a metal, another one is a non-metal. Metal, of course, is the one with positive charge. Non-metal is the one with the negative charge. Of course, in the formula, in the final formula, you can see that charge is not shown, right? We don't show the charge in the formula. We show the charge here, but we don't show the charge in the formula. But these formulas, these compounds we have done, contains what? A metal and non-metal, 2 elements. And we call these compounds binary ionic compounds. Okay, we know they're ions, they're between metal and non-metals. And they're 2 elements, so they're called binary ionic compounds. Okay, they're very common. That's one of the most commonly seen ionic compounds between a metal and non-metal. In this class, the first half, we're basically more than first half, we're going to study these binary ionic compounds. But the first thing we need to study is how do we draw the formula? We don't have to show the reaction all the time, or just ask. If you're asked to do it, you have to show the reaction. But you don't have to know the reaction to be able to write the correct formula for these binary ionic compound. And here is the 5-step rule. It looks 5-step, trust me. After a few practice, you don't even need to look at the rules again. These rules just put in there for you, the first readers, first time you see them. But it's a good start. After you try a few, again, you won't need the rules. Okay, how do we write a formula? First step is you write the symbol of both metal and non-metal. Of course, the metal comes first. Okay, metal comes first. Then you put the charge, okay, on the metal and non-metal in a discrete way, like use a pencil to put the charge. You don't have to really mark the charge. You don't have to write the charge, but you know they will become charged species. So you use a pencil to mark the charge of the metal. For example, magnesium and oxygen. The magnesium charge is 2+, okay, group 2 element. Oxygen, the charge is 2-, group 6 element. So you make the charge. You need to know the charge. Okay, that's the most important thing. You need to know the charge. Now, here comes the most important step. The charge without the sign will become the subscript of the other. So that means the charge of the magnesium 2 becomes the subscript of oxygen. And the charge of the oxygen without the sign becomes the subscript of magnesium crust. The charge becomes the other, subscript of the other. The charge becomes the subscript of another. Charge of magnesium without sign becomes the subscript of oxygen. The charge of the oxygen without sign becomes the subscript of magnesium. So the formula is Mg2O2. We're not done yet. If this is the case, you have to reduce the subscript to the smallest whole number ratio. Because 2 and 2 ratio can be reduced to what? 1 and 1, 2 and reduce 1 and 1. If that's possible, you have to reduce to the smallest ratio. So the formula, correct formula, is MgO, not Mg2O2. Okay, Mg2O2 is not a formula. You have to reduce to the smallest ratio, if reducible. Okay, the same idea, the bottom example, calcium and oxygen. Calcium, the charge is 2. Oxygen is charge is 2. Again, you mark the charge somewhere. You don't have to show like I'm doing here. Here, I have no way to mark the charge. But you can use your pencil to mark the charge on metal and non-metal. Then the charge of the non-metal becomes the subscript of the metal. The charge of the metal becomes the subscript of the non-metal. And then reduce to whole number ratio 1 and 1. That's the formula of calcium oxide. Okay, calcium oxide. And number 5, you can always check. How do we check? We make sure the total charge of metal and non-metal adding together is 0. Or you should say the total charge of the metal equal to the total charge of the non-metal. Calcium plus 2, oxygen minus 2, right? 2 and 2. Magnesium plus 2, oxygen minus 2. 2 and 2, they're equal. Adding together should be 0 because 1 is plus, 1 is negative. So you can always double check. But again, if you follow these 4 steps, especially know the charge correctly, do the cross, you will always get the correct formula. Okay, sometimes you don't have to check if you follow these 4 steps. Okay, here's a couple of practice. And again, I'm even showing you the logic. How do we do it? The compound between sodium and phosphorus. Sodium charge is +1. Here, phosphorus, the charge is 3, -3, because phosphorus is group 5. Okay, group 5, the charge is -3. So the charge of sodium becomes the subscript of phosphorus, which is 1. We don't show that. But the charge of phosphorus without sign becomes the subscript of sodium. So Na3P, 3 and 1, there's no reducible. So the ratio is 3 and 1. So Na3P. Another example, okay, the formula between aluminum and chlorine. Okay, chlorine. Aluminum charge is 3 because it's group 3 metal. Chlorine is 1 - 1 because it's group 7 non-metal. So the charge of 3 aluminum becomes the subscript of aluminum. The charge of aluminum becomes the subscript of the charge of aluminum becomes the subscript of chlorine. The charge of chlorine becomes the subscript of aluminum. So the ratio is 1 and 3. Again, the cross, right? 3 becomes the subscript. 1 becomes the subscript. The cross. Okay, and with that logic, I hope you write the formula for these 3 pairs of ions. So there are 3 ionic compounds. Please write the formula, but don't forget the cross and reduce the number to the smallest whole number ratio. Okay, I think I can have the key in the note area, or I can provide you the key. I can double check with you in our recitation. Please use these as an example. Okay, after that, let's take a look at the structures of ionic compound in a brief way. Okay, structures of ionic compound. We know ionic compounds are made of ions. Okay, made of ions. But ionic compounds, the ions are not individually bound together. They're actually form a huge network called a lattice, like this. Okay, this is part of the lattice. And because of the formation of the huge network of these ions, positive, negative, of this network, ionic compound normally looks very pretty as crystalline solids. Okay, very regular crystals. The reason is macroscopically they look like beautiful crystal. It's because microscopically you're having a crystal lattice, building a very organized network. Okay, network. For example, this is a structure of sodium chloride. Okay, you can see that each sodium ion plus is actually surrounded by some chlorine ions. And each chlorine ion, the bigger one, is surrounded by a few sodium ions. For sodium chloride, the surrounding number is 6. So each sodium is surrounded by 6 chlorine. Each chlorine is surrounded by 6 sodium. And because of that surrounding, the charge and attractions are maximized. And of course, the repulsion is minimized. right? Each positive is surrounded by 6 negative, and each negative is surrounded by 6 positive. So you're building up this whole network. Okay, that's like this. 6 means what? Front, back, left, right, top, bottom. Okay, you're surrounded by 6. Okay, this is the cut line. You can see it's 4, but there's 1 behind and back. And because of that, the ions can stack them together in a very nice way to maximize the attraction, to minimize the repulsion. And also because of that, you notice that in ionic structure, there's no individual molecules existing. You have a huge network with trillions, billions of trillions of ions stacking together. So that is why whatever matters for the formula of ionic compound is simply what? Simply the ratio. Okay, we don't know how many ions are in there, but we know the ratio for sodium and chlorine is what? Is 1 and 1. 1 sodium, there must be 1 chlorine. Okay, a trillion of a trillion sodium must be a trillion of sodium chlorine. The ratio of these two guys must be 1 and 1 because the total charge is 0. So that's why the formula for ionic compounds doesn't matter. It's 2 or 2 or 4 or 4. It has to be reduced to the smallest ratio because that's the only thing we care. That's the only thing we care. And we call the formula empirical formula. Okay, empirical formula is what? The smallest ratio. That's what only we care because we don't have individual formula in the structure. It's a huge network. The formula only tells us one thing. What is the ratio? Sodium chloride, the ratio is 1 and 1. That's what the formula tells us. So the formula is called empirical formula. Okay, empirical formula. Okay, keep moving. After we know the formula, let's take a look. How do we name these ionic compounds? Okay, naming ionic compound, especially these binary ionic compound, follow the rule shown here. You name the metal first, just name of the metal from the periodic table. What is the name of the metal? Followed by the stem name of the nonmetal and the suffix IDE pronounces ide. Okay, so there comes 2 parts in the name. One part is the name of the metal. Another part is the stem name or base name of the nonmetal plus the IDE. So the only question is how do we know the base name and plus IDE for the nonmetals are, which is listed in this table. See that? Bromine. The stem name will be brom plus ide will become bromide. Carbon becomes carbide. Chlorine becomes chloride. Fluorine becomes fluoride. Hydrogen becomes hydride. Iodine becomes iodide. Nitride, oxide, phosphide, and sulfide. You can see these are the names that the nonmetal becomes. Okay, all have a stem or base from the name of the nonmetal plus the suffix IDE. Okay, ide. But the metal name is the same, just name of the metal. So that's how we name the binary ionic compounds with only 2 elements, metal and nonmetal. For example, potassium chloride. Name of the metal, potassium, followed by the chloride. Magnesium bromide. Calcium oxide, right? Oxygen becomes oxide. Now, the naming itself is very simple. It's very straightforward. But there are some metals, especially transition and inner transition metals, such as copper, iron, manganese. These metals, they don't have a fixed charge, or we should say they have multiple types of charges, okay, when they form ionic compound. For example, copper. They could be copper 2 or copper 1. So copper 2 and copper 1, +2 and +1, we'll end up with two types of ionic compounds. If copper 2, the ionic compound will be CuO. If copper 1, the ionic compound will be CuO2, Cu2O. See that? The same here, iron could be iron 2 or iron 3. If iron 2 with chlorine will be FeCl2. If iron 3 will be FeCl3. So you see that for these elements, for these metals, because of the multiple charges, when they make ionic compound with nonmetals, they come in different formulas, different types of ionic compound. And these ionic compounds are actually different. So how do we tell the difference? If the ionic compound is between metal and nonmetal with different charges, the solution is simply incorporate the charge in a parenthesis using Roman numbers. Okay, using Roman numbers. For example, the two on the left, they're both copper oxide, but the first one is copper 2 oxide. You can see that there's a 2 in parenthesis. And the second one is copper 1 oxide. You can see there's a 1 in parenthesis. So we use a parenthesis and the Roman number to tell the charge. Then we can distinguish these two types of compound. Again, copper 1 oxide, copper 2 oxide are two different compounds. The same, this is iron 2 chloride, and that is iron 3 chloride. We use a parenthesis and Roman number to indicate the charge. And here is one question. How do we know the charge? Okay, some metals like these metals, we even don't study them systematically, right? We only studied main group elements, group 1A through 8A. We didn't study B groups. How do we know the charge? The charge of the metals can actually be easily calculated using the nonmetals. Remember, we always know the charge of the nonmetals, right? Group 5 nonmetal charge is -3. Group 6 metals nonmetals charge is -2. Group 7 nonmetals charge is -1. So we can calculate the charge of the metal using the nonmetals because the total charge of metal plus nonmetal has to be what? Has to be 0. If that makes sense. For example, CuO. I don't know the charge of the metal, Cu, but I know the charge of the oxygen. Oxygen charge is -2, so the copper will be what? +2, 1 and 1. So this one will be copper 2 oxide. Here, oxygen is -2. So copper, it will be +2. But there are 2 copper, so each copper is what? Each copper is +1. Remember, oxygen is -2. Copper is +2, but there are 2 coppers, so each copper is +1. So the name of this guy will be copper 1 oxide. The same, copper and bromine. Bromine charge is -1 because bromine is group 7 element. So this copper is what? +1. -1 +1. So this is copper 1 bromide. Here, iron and sulfur. Sulfur is -2 because sulfur is group 6 element. So this iron is what? Is +2. +2 -2. So this is iron 2 sulfide. See that? So we can always calculate the charge of the variable charge metals with the help of the nonmetal. And also we know the total charge of the compound is 0. So I leave the last one for you. Lead 4 oxide, you're gonna calculate why the charge of that lead is +4. A lead 4 oxide, you do some practice and calculate how do we figure out the charge of the lead is +4, right? Finally, when we have a ionic compound, if we want to name them, how do we know? Okay, how do we know the metal comes with fixed or variable charge? Or in another word, how do we know we need a parenthesis with the charge or not? Remember, if your metal has a variable charge, if you don't include the charge, the name will be wrong because we don't even know which compound you're talking about. So you have to know which metal comes with fixed charge. You don't need the parentheses. Or which metal comes with variable charge. You need a parenthesis with Roman number. You have to know that. And here, this table will help you. The metals shown in this charged table, the blue box, are the metals with fixed charges, meaning that ionic compounds with these metals, you do not need a parenthesis, okay, without the Roman number in their parentheses. Other metals, not shown on here, will most likely include their charge in their parentheses. Again, if an ionic compound has a metal with variable charge and you fail to include the charge in the parentheses, the naming will be wrong. How can we tell if we need a Roman number or not? Look at this chart. If it is the metal on this chart, then you do not need a parenthesis because these metals are the one with fixed charges. And of course, metals not shown on this chart, like these ones, are the metals with variable charges. I just want to show you how many charges each metal may have. Okay, these are the common metals with variable charges. All right, so with that, I leave this for you. I don't tell you which metal has variable charge, which metal has fixed charge. You determine by yourself. If it is a metal with variable charge, can you calculate the charge based on what we have taught so far? So name each of the following compound, and you can always ask me to check if you answer right. Email me, post on Blackboard, or ask me a question during recitation. But again, ask yourself first, is this ionic compound containing a metal with fixed charge or variable charge? Last part of this lecture, we're going to discuss a group of ionic compound containing polyatomic ions. Okay, this is one of the very abstract part of this lecture. Some of you have heard of it, but some of you may have never seen these. We know ionic compounds are made of ions, but in nature, there are some ions that are made by a group of atoms, not a single atom, not like chlorine, oxygen, or sulfur ions. These ions here are made by a group of atoms held together by covalent bonds. Okay, we're going to see the structure of them when we study chapter 5. But these ions are bigger because they're made a group of atoms. So we call these ions polyatomic ions. Polyatomic ions are very stable. They never split, they never break down. They generally maintain their identity during any chemical reactions. Here, I show you 3 compounds with polyatomic ions. Of course, the polyatomic ions are highlighted in red, such as sodium hydroxide. You can see OH is a polyatomic ion made by 2 atoms, ONH. Magnesium nitrate, NO3, is a polyatomic ion made by N and 3 O's. NH4SO4, ammonium and sulfate, made by 2 atomic ions, polyatomic ions. NH4 is a polyatomic ion made by N and H4. SO4 is a polyatomic ion made by S and O4. So you can see that these are polyatomic ions. They're just bigger, but they're ionic. They're ions. They're single ions. It's just a little bigger. The reason they're bigger because they're made by a few atoms bonded together. And these are the charts. I think in your book, table 4.3 listed the formula and the name and also the charge of these common polyatomic ions. You can see each ion comes with the formula, means how many atoms are in there. What's the formula? And also each ion comes with a charge, and also each ion has a unique name. They're classified in this chart by the main nonmetal atoms present, such as nitrogen containing one, sulfur containing one, phosphorus containing one, carbon containing one, chlorine, hydrogen, and the metals. Okay, these are the most commonly seen polyatomic ion. But again, each one has a formula, has a name, has a charge. Okay, has a charge. One of your lab naming ionic compounds will have a very full inclusion of these, a lot of polyatomic ions. I hope you take advantage of it, because knowing these polyatomic ions, using these polyatomic ions takes some practice, because by pure memorizing them, it's going to be very time consuming and hard. But use these ions in practicing naming, drawing structures, will get yourself memorizing these faster. But bottom line is, you have to use these polyatomic ions, knowing their charge, formula, and name. Okay, and name. Okay, again, I'm going to go over some of the examples when we study them, but you have to use your way of memorizing these polyatomic ions. There are a lot of YouTube videos helping, maybe created some more efficient way of memorizing them. It's up to you to choose which method you want. Okay, but this table is a very useful table. Okay, now, like I said, we have something to talk about these ionic compound and tell you more about ionic compound containing these ions. The first thing is, how do we draw the formula for the ionic compounds containing polyatomic ions? The way of writing the formula is the same as we have just learned for binary ionic compound. Charge, charge, charge becomes the subscript, charge becomes subscript of another, reduce the smallest ratio. The rule is the same, but again, the only difference is you're not looking at a single ion, you're looking at a more complex ion. Okay, for example, sodium and hydroxide. Okay, sodium is plus, hydroxide is minus. So the charge of sodium becomes the subscript of hydroxide. The charge of hydroxide becomes the subscript of sodium. So the formula is NaOH. Next one, magnesium and nitrate. Magnesium is +2. Nitrate is 1. You can see that. So the charge of magnesium here, charge of magnesium is 2, becomes the subscript of nitrate. Now, because nitrate has a subscript 2, here is something very unique. You have to put a parenthesis of nitrate to indicate what? 2 of the nitrate, because the subscript of the whole nitrate is 2. So here, if the subscript of a polyatomic ion is 2 or more, you have to use a parenthesis, then the subscript. Again, the magnesium charge becomes the subscript of nitrate. Of course, the charge of the nitrate without sign becomes the subscript of magnesium, which is 1. Again, for polyatomic ion formula, if the subscript is 2 or higher, you have to put a parenthesis, then the subscript. If the subscript is 1, you don't have to parenthesis, right? Here, ammonium and sulfate. Ammonium charge is 1, so the sulfate subscript is 1. The sulfate charge is 2, so the subscript for ammonium is 2. You can see that I put a parenthesis of the ammonium, then put 2 outside the NH4. Okay, NH4. The rule is the same. Okay, rule is the same. Okay, here, ask you a quick question. Ask you, what is the formula between ammonium and carbonate? Okay, ammonium is 1, carbonate is 2. So the carbonate charge becomes the subscript of ammonium, right? Charge of 1 becomes the subscript of another. So the carbonate determine the subscript for ammonium is 2, right? Subscript for ammonium is 2. And of course, ammonium charge becomes the subscript of carbonate, which is 1. So this is the formula of ammonium carbonate. Okay, ammonium carbonate. Carbonate becomes the subscript. And of course, for ammonium, because the subscript is 2, you put a parenthesis followed by 2, the subscript. After that, okay, last thing is name these ionic compound containing polyatomic ion is also very straightforward. All you need is to modify the naming of binary ionic compound using the name of the polyatomic ion. Okay, polyatomic ion. For example, we know this is sodium chloride. Okay, sodium chloride is binary ionic compound. Based on that, we modify it depending on whether your positive ion or negative ion is polyatomic. The first example, replace sodium with ammonium. Okay, replace the sodium with ammonium, which is the positive ion. So the name becomes ammonium chloride. See that? Just replace the name of sodium with ammonium. Very easy. If I replace the chlorine with polyatomic ion bicarbonate, then the name becomes sodium bicarbonate. See that? All you need is to replace the metal or non-metal with the name of the polyatomic ion. Okay, just simple modify. Okay, simple modify. And very straightforward. And finally, if both ions are replaced with polyatomic ion, you just read out the name of both atomic ion. For example, here, ammonium bicarbonate. Okay, ammonium bicarbonate. Sodium chloride becomes ammonium chloride, or sodium bicarbonate or ammonium carbonate. So the naming of this compound is a simple modification using the name of the polyatomic ion. Like again, go back to here. In order to do that, in order to write the formula with the charge or name this ionic compound, the most important thing is you need to know the formula, the charge, and the name of these polyatomic ion before you can move on. That's why I said practice the compounds containing these. You will get used to these polyatomic ion. You will find some trend to learn or memorize these polyatomic ion. For example, out of all these polyatomic ions, only one of them is positive, NH4 plus. Okay, that's called ammonia. The other ones are all negative. Okay, this one is positive, but this one really doesn't get involved in a compound called hydronium, but this one is not really forming a compound. So the only one that's an ionic compound that is positive will be ammonia. The other ones are all negative. And also you will find some trend, okay, about the formula, the name, and also the charge, okay, about the charge. Okay, and finally, I think we have to practice here. Okay, I want to go over the second one with you. Practice this one. You can find the answer very easily. Again, use it as a practice, not just choose the answer. And name each one. You will find which one is correct, which one is not correct. Here, I want to practice one with you together to show you as another practice. Okay, and the question asks us to name the compounds or write the formula, okay, for 1, 2, 3, and 4. So let's take a look at each one of them. The first one is sodium and bicarbonate. So the name of this one is sodium bicarbonate. Okay, number 2 is magnesium and bicarbonate. So the name is magnesium bicarbonate. Okay, the third and fourth one, they ask you to write the formula. So we need to write the metal, sodium, and we also need to write the polyatomic ion, phosphate. Okay, this is PO4 is phosphate. Okay, PO4 is phosphate. And then we put the charge, sodium charge is 1, phosphate charge is -3. Okay, phosphate charge is -3. And then the charge of the phosphate becomes the subscript of sodium, and the charge of sodium becomes the subscript of phosphate. So the formula is Na3PO4. No parenthesis, because the subscript of phosphate is 1. Right? That's the formula for sodium phosphate. Okay, let me erase that and form the last one, magnesium phosphate. Magnesium formula is Mg, phosphate is PO4. Again, okay, the charge for magnesium is 2. The charge for phosphate is -3. So the charge of the magnesium becomes the subscript of phosphate. The charge of the phosphate becomes the subscript of magnesium. So we got Mg3PO4. And now you need a parenthesis because you have a subscript of the phosphate too. So Mg3PO4 parenthesis 2. That's the formula for magnesium phosphate. Okay, here, by the way, where is phosphate? You can see that phosphate is one of the ions with phosphorus, PO4, 3 minus. The charge is 3. Okay, charge is 3. Again, for studying these, I know it's a lot of info, but you have to know the charges, the names, and also the formula of these ions in order to name and write the formula for the ionic compounds containing these polyatomic ions. They're just ions, just a little bigger than our simple ions we have seen in the first part of this chapter. All right, that is all for this chapter, and hope you practice a lot more, and we will see you in chapter 5. Bye now.